Today, let's look into some of the most common memory corruption errors in C++ and how we can debug them using Xcode. Um, so here I have written a simple heap buffer overflow case where I have allocated 10 bytes of memory in line number 15, and at line number 18 I'm trying to read right into the 100th index, which is a heap buffer overflow for write ss, and at 19 I'm trying to read from the same location. Let's try running this and see what happens. So as you can see, it is printing letter A, which I have written in this line number 18, but we know that that memory location was not assessed and the heap buffer overflow went undetected. Now how can we detect this? Well, Xcode provides us this its cool debugging feature is that you go into this edit scheme and run tab diagnostics. You have this option to enable many memory management tools. So if we were to enable this guard malloc here, what it's going to give us is, let's try running this again. So it is going to give us bad access for this memory location. But let's try going ahead. If you want a more informative message, and then what you can do here is, instead of guard malloc, you can have this address sanitizer enabled. And let's try running this now. Perfect. So now the address sanitizer gives us that a heap buffer overflow has happened on so and so memory location, and you can even, by pressing on this RAM tab, you can see the memory snapshot for that location too. Okay, now let's look into some more scenarios. So let's quickly look into the underflow case where we are trying to assess the buffer location, which is negative. So it's not as common as overflow case, but still let's try that with the address sanitizer enabled. Yeah. So yeah, sanitizer is able to pick up on that too. Now let's say we are trying to allocate a large chunk of memory into the heap accidentally. In that case, let's see what happens. So let me just comment this heap abuse here and run this. Yeah, so the sanitizer is even able to pick that up, and it's gonna give us this info message that we have exceeded the maximum support size for this project. Now moving on to another common scenario, double freeing. So double freeing happens when we have a memory location as and we have freed it, but we are trying to free it again. So yeah, let's see what happens in this case. Perfect. So the sanitizer is able to provide us this info that we have done a double free. So normally, to prevent this double freeze happening in production code, you almost has to make sure that you never have dangling pointers lying around. Always initialize them to null ptr, and soon after freeing them, make them null ptr, and we won't have this issue from there on. Let's try running it again. Yeah, the program successfully executes. Now let's look at another scenario. Let's try to see use of you're trying to assess a location after it's being freed from the heap. Let's look into that case. Even for this case, the sanitizer is able to provide us the info that we are using a freed location from the heap. Yeah. So that's the most common errors that occur in the heap. Now let's look into what happens in the stack memory. So here I have a typical example of a stack overflow happening where I have a non-terminating recursive function. So the stack is going to get overflowed. Let's see what happens. Yeah, so we can see that some bad SS is being thrown to us, but and we can see the stat trace being abused here. So but the problem here is that the sanitizer is not exactly able to pick this up and give us the right info. However, it is able to do the compiler is able to give us this info that all the paths through this function will call itself, which is a compile time warning, so we can use it can be a helping hint to prevent such scenarios. Another thing you can do is try writing the iterative implementation, which is less likely to run into stack overflow issues. Now let's look into trying to allocate a large chunk of memory into the stack. Yeah, so this is also giving us an execution for a bad instruction. Still not that very useful, but yeah, we can get some sort of a hint for with such info. Another scenario is that we are trying to return address location in the stack from a function. Basically, the stack location get invalidated after a function call, and they are implicitly being freed. So if we try to use this location further, let's do that. Let's see what happens. Yeah, because I have the sanitizer enabled, it's able to give me that a stack use after return is getting detected in this case. So yes, now I have a the mismatch deallocation. This is a common problem that happens in production level codes. So the typical rule is that for each malloc and calloc there should be exactly one free, and for each new or the bulk new operator there should be exactly one delete or bulk delete operator. And for stack allocation, as we have seen before, they are implicitly getting freed from the memory, hence no explicit freeing or deletion should happen for memory in the stack. Now what you should not do is that allocate a memory using new and then trying to free it. This is an undefined behavior, similar for the vice versa case where you malloc a memory and try to delete it. So let's see what happens when we try to run this. So yeah, unfortunately these three cases they don't get detected even with the sanitizers enabled. So keep that in mind and always make sure that you are not doing this mismatch deallocation. However, for the memory location in the stack, when we try to free it, the sanitizer is able to give us the info that is we are attempting to free an address which is not malloc, which means it's not allocated in the heap. Yeah, so yeah, finally Let's look into a complex scenario where an invalid stack access can happen. So it's called cross stack access. What happens here is we have a thread and we have a global pointer called ptr, and we have allocated this ptr some memory in the heap uh, in this thread, and in a second thread we are trying to modify that location. This is not possible because the stack of one thread cannot be accessed by another. So let's try, the stack memory of one thread cannot be accessed by another. Let's try running this. Yeah, it gives us this bad access. So be wary that you don't share the stack memory within the threads, as the sanitizer is not able to pick this up, and it was going to be hard to debug such scenarios. So yeah, that's pretty much covers a lot of scenarios, common scenario of memory corruption in C++. So let me just have this here. So these briefly jot down all the cases that we have seen here for the heap memory errors and stack memory errors. So the way Address Sanitizer works is that it replaces the malloc and free function with custom implementation that allow regions surrounding the requested memory to be checked for invalid access. So what it cannot do is it cannot detect memory leaks, access to uninitialized memory, or any sort of integer overflow. So yeah, so I think that was helpful for some of you guys who find this hard for debugging such memory issues. Thanks again. See you again for next time.